Okay, last section of chapter 3 that we're going to cover, and it's called optimization. So basically, the idea is we're trying to maximize or minimize something. Okay, so what you're going to see, I'm going to do a couple of problems. I'm going to maximize the area in a little bit. I'm going to minimize distance. Okay, so these are the two problems that I will work. These are examples. But you're always wanting to maximize and you're always wanting to minimize. That's what optimizing is. So maybe give the dimensions that give a maximum area. What's the coordinate that will minimize distance? Something along those lines. These are examples. Okay, so for example, so for those, i.e. area, distance, we could maximize profit, maybe minimize cost, maximize volume, but minimize surface area. Why might you ever want to do these together? Maximum volume, but minimum surface area. Yeah, you got the idea, right? I mean, coat, you like talking about paint? Is that what yeah. So for instance, the larger, if you're wanting to paint something, you're painting the surface area. The larger the surface area, the more paint you gotta use. The other way, just think of the material that it costs to make that surface area. So maybe you're trying to design a tank to hold extra gasoline for a jet, right? You want to maximize the volume, but you want to minimize the surface area. You also want to make it aerodynamic. So there's a lot more to that, but you get the idea that surface area might lead into cost. And these are things that you want to minimize. So there's a whole list of things, but optimization falls under those categories. Either you're maximizing something or you're minimizing something. Okay, so that's the first thing you're going to do. All right, so I've got a pretty generic problem, and then we're going to work one area and one distance problem for today, and just to wet your beak a little bit and get you going, and then we'll do more problems tomorrow. So my first strategy. So I've got the example 1 on the board there. Find the two positive numbers that satisfy the requirements. The sum of the first number and twice the second is 112, and the product is a maximum. Okay. So my strategy for optimizing. There we go. So the first thing I'm going to do is read and take notes. And I'm going to take math notes. Okay, I'm going to start to create and label things. So if you're talking about two numbers, I'm probably going to call one number X and one number Y, since I don't know what they are. So I'm going to read and take notes. I'm going to start to label. So as I'm going to label what I know maybe and don't know. And the other thing that I need to determine is, this is the big question here on number 3. What are you trying to maximize or minimize? Because that's your equation that you're going to have to write out. What are you trying to maximize or minimize? Now, so that's the key question you got to ask yourself. So figure out what it is and then write an equation for that. So after you've determined that, then write out an equation for what you are trying to optimize, to maximize or minimize. Now, there's a good chance that you could have two unknowns on the right-hand side. So we're going to have to use other information to make sure that the right-hand side only has one unknown. You don't want to have two unknowns on the right-hand side. So use other information in the problem to make sure your equation is in terms of one unknown. And then after you get that, after you get whatever it is that you want to maximize or minimize with one unknown, then you're just finding the relative max or relative min. You're just doing what we've been doing. So you use whatever first or second derivative test to find relative max or relative min. So find use first derivative test. Okay. All right. So that's the strategy that I would use. So as we work this problem, we're going to work the three problems. We're going to leave that there and make sure that that strategy works. Okay, that we're going through the steps and that it makes sense. Maybe we need to add or take out a step. We can talk about that. Okay, so I'm going to read the problem. It says find two positive numbers. They didn't say integers. It says positive numbers, real numbers. So could be a decimal that satisfy the requirements. The sum of the first number and twice the second is 112, and the product is a maximum. Okay. So the first thing I want to do is, I don't know the two numbers, so I got to label them somehow. What are usually the two variables you use most of the time? X and Y. So what do I know? So here's give me information. The sum of the first and twice the second is 112. Okay. So my two numbers are going to be X and Y. So I'm going to try to take whatever the information is here and write it out. Okay, so you can probably make an equation with this part. And then here, you'll notice it's telling you what we want, how we want to optimize it, what we want to know about those two numbers. So it has to meet two criteria. One is it has to do this. I got to take a number, multiply the second number by 2, and I add them up. I should get 112, whatever that is. Okay, whatever those two are. And then what else has to happen? Whatever those two numbers are, when you multiply them together, you got to get a maximum. So there's a lot going on. So the first thing I would do is, can you take up to this semicolon and write that as an equation? See if you can make that equation. So go ahead, using our X and Y, make that equation there. Up to the semicolon. Okay. Now notice nobody said anything about maximizing or minimizing there. We're just trying to take those words and make it an equation. Okay. So what equation can you write right here?
X plus 2y equals 112.
All right. So X plus 2y is 112. So let's refer to my notes right now. I'm reading and taking notes. I'm labeling knowns and unknowns. So right now my unknowns are what? What do we not know? The X and Y, the two numbers. That's what we're trying to find. We're using this is algebra, basically. Okay. Now, what are we trying to maximize or minimize? They're so nice, they tell us. Their product. Well, how do you write that out? How do you write the product of two numbers? Yeah, so what I'm going to do, I have to make another equation. I'm going to say P, because that's what I'm looking for, product, is XY. This one may be hard for you, but you have to call it something. See, so it's a product, so I got to do that. So now, so this is where I'm going to highlight because you're getting a lot floating around. Remember, what are you trying to maximize or minimize? I'm trying to maximize the product, because there's a lot of numbers that you can do this to. See, there's a lot of numbers that you take a number and you double another number, and can you get them to equal 112? There's a lot. Okay, so we could play around with it on our calculator, and just, like if I put 10 here, right? Put a 10. 10 plus 2y is 112. 2y is 102. So y has to be equal to 51. Now I got my two numbers, 10 and 51. Multiply them, I get 510. That's their product, okay? There's one. All right, now maybe I pick 20 for the second number. 20 plus 2y is 112. So 2y is 92. So y equals 46. So now I got 20 times 46, whatever that is, 920. Now that's a bigger product. We can do this forever. That's why we're going to use math to just solve it one time. But you get the idea. So I found my two numbers, 20 and 46, meet these criteria, because I just picked one and solved for the other one. Okay. All right. So we can't do this forever. I already know 20 and 46 were bigger than 10 and 51. Here I did 10 and 51 were the two numbers that meet this requirement, and that's their product. So I don't want to keep doing that. It's going to take a while. All right, so, okay, so we want to maximize their product. But remember what I said. So write an equation for what you're trying to maximize or minimize. Well, their product, so you multiply them. But notice, it says use other information in the problem to make sure your equation is in terms of one unknown. Remember, when we've done calculus this whole year, we haven't had x's and y's on the right-hand side. We typically have just had x's or maybe just y's. We just want one variable on the right-hand side. We don't want two. So now you've got to use other information in the problem to write this equation with one unknown. Now it might be easier to solve for x. See, x is already by itself. You could do that and make this just y's over here. Well, that means we're finding the same. It doesn't matter. So solve for one of these, whichever one you want. Either solve for y or solve for x and plug it in. Now you got one equation. Okay. I mean, I'm sorry, one equation, but one what? What do we want over here? One variable on the right-hand side, because then we've got to do relative max and min, which we know that process. Okay, so pick one and either solve for x or solve for y. I would just solve for x, it's the easiest, and then substitute in right over there. You can, it's up to you, you can do either one. Okay, so which one's the easiest one maybe? What's the easiest to isolate? X, right? So x, we're using this other equation. X is 112 minus 2y. So then I'm going to take that and replace x with 112 minus 2y. That's going to go there. So x is 112 minus 2y times y. And now we have an equation with just one unknown. Okay. So now what we're going to look for is what does y need to be so that this is a maximum, okay, because we want to maximize. So at this point, now so this was step 4, right here, we have our equation, and now this is step 5, where we've made our equation with one unknown on the right-hand side. Now the last step, I would probably distribute my y there and make it 112y minus 2y squared, right? So I don't have to do product rule. Now, do how you normally do your first derivative test. So do your first derivative test to get maxes and mins. So you're going to do first derivative test. Remember all the steps. You need your critical numbers, right? So you got to take the derivative, set it equal to 0, put it on the number line, and you should get a value for y, and then you should see if it actually does produce a maximum there. So just do your first derivative test for that equation now. catch up with you, see. So I'll do P prime, I get 112 minus 4y. If I do the derivative, set it equal to 0. 112 equals 4y divided by 4. Y equals, so what's 112 divided by 4? What do you get there?
28.
28? That's right. So there's your y. Now, I would just put it on the number line real quick to make sure that it does produce a maximum. So I would test on the right and left. So if I plug in a 0, my first derivative, so I'm plugging into P prime is positive, which means the graph is increasing. If I plug in a 30, say I plug in a 30 here, I get a negative answer, which means it's decreasing. So I'm just verifying that it's a max, produces a maximum. All right, but what did the question ask for? Find two positive numbers. Well, how do I get the other number?
Plug Y back in.
Yeah, over here, you know, here's x is 112 minus 2y. Now I got to go back and sub in to get my x. So x is 112 minus 2 times 28. So 112 minus 56, which should be 56. So x is 56, y is 28, and those are two numbers whose product is a maximum. And they satisfy this little condition here. Yeah. And that's your first problem. Okay. All right. Now I'm going to leave our recipe, but I'm going to erase the work here once you guys are ready. We'll write the next problem now. So I'll start writing the next problem, and then I'll give a picture that goes with it. Sometimes you won't get a picture. You'll have to make the picture yourself. Okay. A farmer has two adjacent rectangular pens. Well, he's trying to make. So a farmer wants to make two adjacent rectangular pens with 600 feet of fence. What dimensions should the farmer use to maximize area? What is the maximum area? Makes sense that the farmer probably wants to maximize area. Probably he or she is putting maybe something kind of cattle or chickens or pigs or something in there. So here we go. So now what we're going to do, you can see it is clear what we're trying to maximize or minimize. Now I'll give you the drawing for this because sometimes it's hard to understand. So they're going to be equivalent in size, like this. So each pen is identical, okay? So now you can see you have basically one big enclosure with a partition. Maybe this is trying to, what's the word I'm looking for? Separate the two different livestock or something like that, okay? So go through the steps. I've given you at least a picture now, so you got the picture. But remember, you need to collect all the information that you can, and you probably right from the start can write out what it is you're trying to maximize or minimize, but there's still plenty of information. so since we're filming this and we're just trying to get you going in the concept, I'm gonna kind of work along with you. So I kind of work here first. I'll figure out what is it I write that equation first. I know that I'm trying to maximize area, so I'm gonna write the area for this. Well, what's the area of one of the pins?
X,
XY, but how many pins are there? 2, so it's gonna be what? 2xy. So I go straight to step 4, write out an equation. And now, but I see that it has two unknowns on the right-hand side. So now I know there has to be other information in the problem somewhere that I need. So now I'm gonna go back to step 1 and read and take the notes. I mean, I've already read it, but now I'm gonna start writing everything out. So 2 adjacent rectangular pins with a 600 feet of fence. All right, so once I see this, 600 feet of fence, this, all that has to add up to 600. So I'm gonna create another equation because I know I need another equation to solve for one of these. So basically, what is that called when you add up all the distance around and all that? That's called what? Perimeter, and you have that partition there. So what's the perimeter? Including partition, what would it be? 4x and 3y. So now you know 4x plus 3y has to equal to 600. So that's the other bit of information I have to have. Because this is my equation. I want to maximize area. But I can't maximize area with an xy. So now I have to use other information in the problem, and I'm usually will solve for y. We'll substitute for y, as I like working with x. Doesn't matter. Either way, I'm gonna have to divide by 3 or divide by 4. So what I'm gonna do, I'm gonna use, so notice what it says, use other information in the problem to make sure your equation, so what do I mean by your equation? What it is I'm trying to maximize or minimize is in terms of one unknown. I have 2 unknowns. So I pick one variable and solve. So I'm gonna solve for y. 3y is 600 minus 4x, divide by 3, and I get y is 200 minus 4/3 x. And now once I get that, I can replace my equation here with y. Replace the y with 200 minus 4/3 x. So I get 2x, so I get area is 2x times 200 minus 4/3 x. Okay. And now I'm basically at my last step. I'm ready to go. I might do one more thing before I do my calculus. What might it be? Same thing I did on the other problem. Distribute. Yeah, I want it expanded. So that's 400x minus 8/3 x squared. And now it's ready to go. And now you can do your first derivative test. Okay, so I'll catch up to you here. I'll take the derivative, I get 400 minus 16 thirds x. I'm gonna set that equal to 0 to get the critical numbers. So 400 equals 16 thirds x. Cross multiply 3/16. So 3/16 times 400 equals to x. Let's see. I can cancel 4, that leaves 100. So I got x is 75. Does that look right? Is that what you guys got? Okay, now here's what I could do. Here's where the second derivative, because I gotta see it, this should produce, this should be at a peak, right? It should be at, we're looking for a maximum. So I could use second derivative test here on this. So here was my first derivative. If I find my second derivative, I get negative 16 thirds. Well, since my second derivative is always negative, it tells me that the entire graph is concave down. Well, if the entire graph is concave down, and at 75 the slope is 0, then I know it's a max. That's the second derivative test, okay, that we studied back in 3-4. So I can see that 75 is going to give a maximum. So what else do I need to find? Well, I got to also find my y. Okay, so let's see. I'll go back to my other, where the other information was, and I'll sub my 75 in to get my y. So y is 200 minus 4 thirds times 75. 3 goes into 75 25 times, 4 times 25 is 100 minus, or from the 200, I get y as 100. And I had x is 75. Let's see if that makes sense. 1, 2, 3, 300. 75 and 75 is 150. 75 and 75 is 150. That adds up to 300. 300 and 300 is 600 feet of fence. And now, what is the maximum area? Well, one of these is 7,500 units if I multiply. So both of them together are 7,500 units, which is pretty nice there, right? Yeah, it's good. That's a good area. 15,000. Okay. Okay. So my dimensions, so if I answer this, dimensions. So for one pen, x is 75 feet, y is 150 feet, and then that's for one. And then total area is 15,000 square feet. Okay. All right. Okay, one more problem. You're going to see the problem that you're going to face is every problem you get to is a little different. And we went from adding numbers and multiplying numbers to now we got a rectangular pens. Now we're going to have a graph that we're going to look at. Okay. All right. So this is on the video, so we can always go back, use the video to help us. We get lost on something, work it again. All right, last problem for today, and then of course we'll work more tomorrow. All right, example 3. Now we're going to get a minimize, okay? Okay, let's see. Find the point on the graph f of x equals x cubed that is closest to the point 1, 0. So here there's an understood maximum or minimum. You have to figure out what it is. It's not in words. So from this problem, you got to read into it what the max or the min is. So I'm going to just draw this real quick so I can visualize it. I know what x cubed looks like. It's this squiggle graph. All right, and I know the point 1, 0 is somewhere over here. There's that. So I've got my graph, and I've got the point 1, 0 not on the graph. So what are we looking for? We're looking for what? The closest point. So the closest point on the graph to the point 1, 0. It doesn't make sense it's going to be up here. I don't think it's going to be anything in the third quadrant. I'm just going to guesstimate somewhere right here. Now, we don't know the point. Okay? But we got to find the point on the graph that's closest to this. What can you call an arbitrary point on this graph? What could you call any point? What's a symbolism you could use for any point on this graph? X f of x, okay? And instead of x f of x, what else could you use? xy, okay, very good. So either one, I might use xy because it's simpler to write, but you're exactly right. It should be x f of x because that's what it's called. Well, we'll do much better than that in a second. So now, what does it mean to be the point that's closest to this point? What does that mean? So this is where you have to use the word maximize or minimize. See, so I'm trying to lead you to it because you're going to have to read this and know, am I maximizing, am I minimizing? And what is it that I'm maximizing or minimizing? Minimizing distance. That's it. We are minimizing the distance from xy on the graph to the point 1, 0. That's what we're minimizing, distance. This distance here. Okay? So, all right, distance. How do you do distance between 2 points? Distance formula. Square root x2 minus x1 squared plus y2 minus y1 squared. That's the distance formula. So I need distance formula for this problem. And I know my 2 points, x, y, and 1, 0. Here's my 2 points. Okay. So sub in your information. So I would probably pick x, y as my second point, y, 1, 0 is it doesn't matter. Either way, sub in your information. But yeah, this is where it becomes tricky because you have to be crafty a little bit in understanding that I have to read the problem and see that this is a minimum distance problem. And a lot of times it'll tell you at the start of the problem, minimize distance. Like it'll title the problem, finding a minimum distance. But I don't want you to rely on that. And we may get stuck a little bit. Like I just made this up off the top of my head. It may be tough to do it analytically, so we can talk about a calculator also. So just sub everything in and see what you get. All right. So what are we trying to maximize or minimize? We're trying to minimize distance. Right now we have a whole lot of symbols over here we're about to replace. We've got our information from our problem. I'm going to go ahead and erase this recipe. I think by now you should have it. Okay. These are all approved. Okay. So if I sub in, It doesn't matter, I'm just, these are my x's, these are my y's, so square root x minus 1 quantity squared plus y minus 0 quantity squared. Now, the only thing is, notice I have my two unknowns over here. But from what Elijah was saying earlier, we know that y is f of x, and f of x is x cubed. So I'm not going to use y, I'm going to use x cubed there. Okay, because y is x cubed. So now I already have all of my, and so this becomes x minus 1 squared plus x cubed squared is x to the 6th. Now, we may have trouble finding our critical numbers. So let's just say that by hand this becomes tough to do critical. I'll show you how I would do it, but let's just say it becomes tough. So let me give you an alternative way where you can use technology to help you. Because remember, we're trying to figure out what does x need to be so that we minimize distance. So graphically, what does a minimum look like on a graph? Yeah, a low point. So we're looking for a low point. So here's what you can do. Just type this into y1. Type in square root x minus 1 quantity squared plus x to the 6th, right? Because if I do x cubed squared, it's x to the 6th. And look at the graph and see if you see a dip in it. And then there's a max and min feature. You can do the second trace and you can pick minimum. And you should be able to find that point. Now, be careful, that's not going to be the point that you're looking for on the graph. We'll talk about what that gives us. So let's use technology, and then I'll talk about how would we have used calculus to do this. You know, what's the calculus that you would do? It's not going to be pretty. All right, does anybody have a coordinate? Did it give you anything? Find a dip?
Yeah, it's definitely not pretty.
What does it tell you? Just round it to like 3 decimals.
Yeah, so for the x, it's 0.651.
Yeah.
Y is 0.445.
But let's make sure that you understand, this is not y. This is distance. Because look at your equation. Your equation is x distance, not xy. So that's the actual distance. But the 0.651 is the x. See? You found the x. You didn't find the y coordinate. I want to make sure that you understand what this point is. Notice that my equation is x comma d, distance. So it gave you the x coordinate and it told you the distance. Now you can get the y coordinate very easily. See? Because it told you the x point, 0.651. Well, how do you get the y? Cube it. Just cube 0.651 and you got your y coordinate. See? So that is x comma distance, not x comma y. So my x is 0.651. So my y is going to be 0.651 cubed, not 0.445. What do you get when you cube 0.6? 0.275. Well, run it to 3, 0.276. Okay, and there you go. And that's the point on this graph that's closest to the 0.10. Now, let's just talk about the calculus that would have been required, because I would have to do what to this in terms of calculus? What would be now I've got all the x's, I'd have to do what next? Make derivative, okay. I would probably just expand everything in here. So if I was going to do the calculus on this, I would make the inside of the square, I would expand it. So that's x squared minus 2x plus 1 plus x to the 6th. And then, so now when I take derivative, remember the derivative of a square root is u prime over 2 square root of u. So the derivative of the inside is 2x minus 2 plus 6x to the 5th all over 2 square root of that thing. So I'm gonna just write it in order, x to the 6 plus x squared minus 2x plus 1. Now, I can tell you this from working these, you don't need to worry about setting the bottom to 0. Just set the top to 0 and see if you can solve it. But you can see it's not easy. Because you got an x to the 5th and an x, you're gonna need technology at some point. But if we solve this equation equal to 0, you're gonna get 0.651. You just say, how do I do this? Well, the problem is now, I can't really do this by myself. So I'll plug this into y1 and see where it's 0, see where it crosses the x-axis. So you may need some technology. So if you need technology, when you get to your optimizing equation, for a minimum, you're looking for a dip. For a max, you're looking for a hill. All right. We'll stop there for today. It's enough for coming back from Turkey. All right.